to this computer. Hello, welcome back. I hope that you didn't have a very stressful testing experience. I only had a few emails, and so that turned out pretty good. Most of you seem to get in pretty well. There was the one thing that happened that was hard to get in was if you didn't enable sharing of your webcam with Proctorio or Chrome, it occasionally will kick you out for that. But I think we got everybody fixed on that. In addition to that, if you do have a broken webcam, I'm going to set up a Zoom monitored version of the exam. So if you don't like Proctorio, I will live Zoom watch you while you take the exam for the next one. So that is an option, but I believe the idea that having actually nobody watch you, yeah, this is Earl Grey tea, by the way. Yes. Okay, so that will be available to you. So I have started running the statistics. The raw average is just over 61, and I'm going to curve that. And so look for those numbers by tomorrow. My father's in the hospital, so I'm not as up on, I meant to have this done yesterday, but I didn't. I apologize. But all of those and your homework grades should be updated in Canvas. Remember, you want to look at your grades in Canvas, not on Top Hat, because in Canvas, the test is actually 120 points. And so you can look for points and percentages in Canvas. The raw score on Top Hat means nothing. So don't worry about that. And because I think because there are 4 different tests, it says you got 65 points out of 400. And so it looks horrible. So don't worry about that. Okay, so we have chapter module 5 today. We're going to finish up module 5 and do a group activity next Tuesday. So I'm going to email out the group activity next Tuesday. All you have to do is come to class, get your breakout sessions, talk amongst each other to try to get, how to do the 2 things. It's going to be over R&S assignment and chirality. We're going to talk about that, plus E and Z assignment. We're going to talk about that a little bit too. So that is where we're going. And then we'll dive into module 6. Module 6, I decided I should give you more homework points in module 6. So there's actually 3 different readings in module 6, and you get 20 points for each of them. So that's hopefully going to bolster some people's grades. And so you'll have, those are some extra points we're going to add to the mix this year. So we'll go ahead and do that as well. Okay, any questions about the exam or what's going to happen today? Okay, so that being said, I'm going to go ahead and share my screen, and we're going to talk about module 5, stereochemistry. Okay, so the first thing I need to say here in stereochemistry is this is really hard for some people. Okay, so you got to practice at it. But if you're really good at Minecraft, this should be really easy for you because it's all about spatialization. So in the case of stereochemistry, stereo actually means space. So imagine you have the exact same molecule, but you have 2 of the bonds swapped, and so they're at a different place in space. That's what we're going to focus on for our stereochemistry set, okay? So we can have a bunch of different types of isomers. So let's go talk about the isomers first, and then we'll get into the stereoisomers second. Okay, so isomers are just different compounds made from the same formula. So C2H10, O5. Okay, you can hook those together a bunch of different ways. And each time you do, you can even have where they have the same connectivity, or you can have different connectivity and have different functional groups. So each of these things, even though they have the same formula, can have those different functional groups, meaning they are isomers. Okay, so we have a variety of different isomers we're going to talk about. We're going to talk about structural or constitutional isomers. And I'm going to tell you the difference between a structural isomer and a conformational isomer when we do that. The next thing is that they're only different in space. They connect all the same way, but they just swapped maybe 2 atoms in their connections. And those are what we call stereoisomers, okay? And we have 2 types of those. We have enantiomers, which we're going to find out are always come in pairs. So we always have 2 enantiomers that come together. And typically they are, when we start with the simple enantiomers, they only have 1 chiral carbon, 1 carbon that has stereochemistry. However, if we have more than 1 stereocenter or 1 carbon with more than 4 things attached to it, we're going to have sets of diastereomers. Okay, And I'll talk about that and how to differentiate between the two. Okay, so let's go to isomers again. Okay, so in this example of C2H6O, we can hook it together different ways. And when we hook it together different ways, we actually ended up with different functional groups. Okay, in this group right here, oops, that's a race. In this one right here, we end up with an ether functionality. So we have carbon, oxygen, carbon bond, and it only has dipole-dipole interactions, allowing it to have its physical properties. Okay, and because of that, that's not a very strong interaction, and therefore it's a gas at room temperature. Okay, and it's a liquid below that, and you have to go way down to like negative 200 before it even freezes. So remember that boiling point is a function of molecular weight plus the types of intramolecular interactions they have. So even though ethanol right here, we've rearranged it. So now we have that alcohol group, that OH can hydrogen bond. Because that OH can hydrogen bond, it now has a stronger intramolecular interaction, and it's actually a liquid at room temperature, even though they have exactly the same mass. Okay, so that's the important there for our isomers. These are what we call structural or conformational isomers. And they have different boiling points and melting points and different reactivities. Okay. Come on, there we go. So let's look at these, another set of constitutional isomers. And when we look at these isomers, we can have just this C5H12. We can do a linear chain right here, or we can do a branched alkane. Now, notice that the linear one has a more surface area and therefore has a higher boiling point because it has more surface area for those van der Waals forces to attract it. Now, when we have this methyl group here, that kind of breaks up the surface area, makes it a little more round, a little more spherical, and therefore it has a slightly lower boiling point, okay, even though they're the same molecular weight. Let's add an oxygen to this and have them all be alcohols. So we have alcohols, so these are all available to us. So hydrogen bonding, so our boiling point should immediately jump, and it does by over 50 degrees. Oh, gotta let somebody in. There we go. Okay. I'm gonna change my view up here to get these people, so I make sure I see that. All right, there we go. But so we all have hydrogen bonding in those, but we can also add our van der Waals forces to it. And so we see a difference in boiling points by how and where we put that alcohol group. So when we have the available van der Waals forces on this side, plus the hydrogen bonding, we have the highest boiling point. And when we break up that surface area, we have a slightly lower boiling point. And when we turn it basically into this, umbrella type thing so that it has very little hydrogen bonding, you can only hydrogen bond very small groups up here, it has the lowest boiling point of the possible. But that's not the only way to do constitutional isomers. We don't just have to move where the functional group is. We can actually change the functional group. So in the case of C4H8O, we can actually make a ketone right here, which again has dipole-dipole interactions. We have an aldehyde here, which also has dipole-dipole interactions. And we have a ether, okay? And this happens to be a cyclic ether. And so it has only available to it dipole interactions and a little bit of the van der Waals forces on just in it. So these are constitutional isomers. Notice they have different functional groups, they're attached in different places, and they have different physical properties. Okay, questions on constitutional isomers? Okay. In contrast, we can also have what we call conformational isomers. Okay. In a conformational isomer, you have the exact same compound, it's just drawn a different way because of a rotation around one of the bonds. So for example here, in the case of this to this, these are constitutional isomers because we've changed the bonds. There's different types of bonds, or those bonds are in different places, okay? For a conformational thing, all we did was rotate around this sigma bond, and we drew it differently. So that's the difference between a constitutional isomer and a conformational isomer. Conformational isomers are exactly the same compound, just drawn a different way. Okay, so let's get into stereoisomers and geometric isomers. So in the case of an alkene, you have that double bond. And because of that double bond, you do not have free rotation. You have free rotation around sigma bonds, but you do not have free rotation around that double bond. So it's fixed in space. Ergo, it has a spatial component, therefore it's a stereoisomer. So in the case of this compound here, if we have the same attachments on both sides, so notice we have a hydrogen and a chlorine attached to this carbon, and we have a hydrogen and a chlorine attached to the second carbon here, and we just swapped the location of the atoms on one side or the other, we end up with a stereoisomer of that, okay? So see how the chlorine's on top here and the hydrogen's here? But notice they have all the same connectivity, it's just where they are in space. So that means you can have cis-trans isomerization is a stereoisomer for the alkene, okay? Now, this is also a geometric isomer because the chlorines are on different sides. And we'll talk a little bit more about the stereoisomers associated with these toward the end of this chapter. Okay, do we see what a stereoisomer is now? It's a change in where it's fixed in space, okay? It's easiest to see on the alkenes, so we're gonna start there. Okay, all right, so, and as we learned already in the nomenclature chapter, we have the easy nomenclature system. I'm gonna quickly review it so that we're aware of it, because we're gonna use the exact same prioritization rules when we talk about the assignment of chiral carbons, okay? So we have that E and Z, which is E is across or trans, Z is together or cis, but we look at each side of the molecule. We find the highest priority group on this side and mark it. Then we find the highest priority group on the other side, mark it, and then based on where they are, if they're close together, we call them zusammen. If they're opposite each other, we call them entgegen or E, okay? So that should be review right there. And to look at our other rules here, if we have our second rule is if you have atoms that are the same on the first try. So if we go out here, we have a carbon, a carbon, a carbon, a carbon. We can't make a prioritization. We then continue to go out further and further and further until we have a difference. So for example, on this side, this carbon only has three hydrogens attached to it. On this side, we have two hydrogens and a carbon, making it higher priority. Okay, so that's rule number 2, and we're going to use that rule as well for our other assignments. Then rule number 3 was talking about double bonds. And so if you have double bonds to oxygens or nitrogens or carbons, we have to count each of those bonds toward that prioritization. Okay, so in the case of something like this right here, this carbon has bonded to one bond to oxygen, one bond to oxygen, and one bond to carbon, giving it that priority. But if we look over here, we have this carbon right here is bonded to 3 nitrogens. Nitrogen is a higher atomic number, and therefore nitrogen is the higher priority. No, oxygen has the higher atomic number. That's right. Oxygen 8, nitrogen 7. So that's why even though there's only 2 of them there, they are ranked the higher priority, and therefore you get the higher number. So that's the third rule. When you have multiple bonds, you have to count each of those bonds toward your priority. Okay, so we're going to use those same 3 priority rules for chiral carbons. Okay, so what is chirality? Okay, by definition, chirality is handedness. Okay, from the Greek word chira, which is talking about your hand. And so that's where actually one really easy way to explain it is that hands are kind of like mirror images, okay? So if you put your hand on a mirror, it's gonna look like the other hand if you look at it. So imagine you put it on the mirror like this, so the thumbs line up, the index fingers line up, and the middle fingers line up, and therefore you have this mirror image of each other. But there's one other rule we have to look for in chirality. When we have these mirror images, they cannot be superimposable. which means that if I tried to arrange it so that I could line up all my fingers on the same way, so I'm going to line up my index finger, my hand, and my wrist right here together. But notice that my thumb and um, middle finger are lined up here. My thumb and middle finger are lined up here. So what that means is my thumb and my middle finger have swapped locations. Okay. So when you're looking for chirality, they first have to be mirror images of each other. And then when you try to superimpose them, two of the atoms are not lining up. The other three atoms line up, but two of the atoms are not lining up. And that tells you you have a chiral center. Okay. It's called a chiral center, a chiral carbon, a stereocenter. All of these are names to where we have a stereoisomer of a compound available to us. Okay. So how do we do our, if we just had a compound and we wanted to see what its stereoisomer might look like, the way to do that is we would draw our stereoisomer, and we're going to do a wedge out here, a solid wedge to show it's coming out of the plane, and a dash wedge to show it's going into the plane of the paper. And the lines right here just signify that we are in the plane of the paper, or in this case, the iPad. Okay, so this one's coming out at us, this one's going behind right here. And I'm just going to arbitrarily number them 1, 2, 3, 4, because when we draw our stereoisomer to make our mirror image and show that it's not superimposable, we're going to draw our mirror right here. And then we start from the closest thing to the mirror and draw that, 3, and we keep the same wedging that we had before. And then we have a solid wedge coming out here at 2. We have our 4 going up, and then our 1 going back here. And now this is how to correctly draw your non-superimposable mirror image. Because when we rotate this around, the 4 and the 1 and the center are going to line up, but the 2 and the 3 are going to be swapped. So what does that look like? Okay, what that's going to look like is something like this right here. And notice that we have the bromine, the carbon, and the fluorine all in the plane of the paper. And this chlorine is sticking out at us, and we have the hydrogen back. Okay, so when we drew our mirror image, it looked like this. Okay, but if we were to rotate this 180 degrees around this way, our fluorine would still be up, our bromine would still be in the plane of the paper, but our hydrogen has now come out toward us because it's wrapped around to here, and our chlorine is now behind. Okay, so if we tried to line up this with this, the chlorine and the hydrogen now are opposite each other, and this chlorine and this hydrogen are now opposite each other. So now we know we have a mirror image because we drew it as the mirror image. We rotated it 180 degrees, and now it's non-superimposable. The hydrogen and the chlorine line up, which is not superimposed because it should be hydrogen over hydrogen. And over here, the hydrogen and chlorine, it should have been chlorine and chlorine if they were the same compound. So that's how we identify our stereoisomers. And if we were to do a ball and stick drawing, it would look something like this. Notice that we have 3 of the atoms line up. The 3 here in the bottom here all line up. We have the bromine, we have the chlorine, but these 2 have now swapped. The chlorine is on the left side, and the hydrogen is now on the right side. So 2 of those atoms have switched places in space, ergo stereo. So this is a stereoisomer, okay? And I'll talk about planes of symmetry in another slide. Okay, so what does that mean? That means to be a chiral carbon, you have to have 4 different things on your carbon. And that's because if you had 2 of the same things, you could make a mirror image, but then you could rotate it around so it looked the same. Okay, so let's start with our compound here. This is bromochloromethane. So we have 2 hydrogens on there. And if we draw our mirror image, notice the bromine right here, straight line, the hydrogen sticking up, straight line, a dashed hydrogen going to the back here, and our wedged chlorine coming out. If we were to rotate this 180 degrees, our hydrogen would be sticking out, our chlorine would be sticking back, and the bromine and the hydrogen would still be in the plane. Okay, so maybe that's hard to see. Let's draw it in the ball and stick right here. So let's look at this. Now we have the mirror image where we have, when we started it, we had hydrogen on this side, and we still have a hydrogen on that side. And we have a hydrogen on this side, and we still have a hydrogen on that side. Therefore, those are perfectly lining up. These three atoms lined up, and those two hydrogens are exactly the same, and therefore they also line up. That means this is not a chiral compound, okay? And we call a non-chiral compound a achiral compound. That's A-C-H-I-R-A-L, okay? So occasionally, if you're talking too fast, you'll say, hey, this is a chiral carbon, or this is an achiral carbon. So be careful how you say it. Sometimes I'll say a non-chiral carbon just to make sure it's clear. Okay, so, but we could have really kind of jumped to a conclusion real quick here, saying this can't be a chiral compound because we don't have four different things bonded to that chiral center, that chiral carbon. We only had hydrogen, bromine, and chlorine. Therefore, we should have known immediately it wasn't a chiral compound. So the first thing to look in chirality is four different things bonded to a carbon. Okay. So the other thing we need to recognize is, especially when we start going to more than one chiral carbon, is looking for what we call a plane of symmetry. Okay. So in the case of a plane of symmetry, this is something, it's an imaginary mirror that you can put through the molecule. It can be either through the atoms or just through bonds. And if it looks the same on one side as the other, then you have a plane of symmetry, and that immediately makes the molecule non-chiral or achiral. Okay, so in this case here, we're actually, we've redrawn it as this cross figure right here. And when we draw our plane down the middle here, half of the bromines on this side, half of the bromines on that side, half of the chlorines on this side, half of the chlorines on this side. And look, these two wedged hydrogens are opposite each other, therefore they are symmetrical. Therefore, we have a plane of symmetry. Okay, and if we were to draw in that three-dimensional look, and we draw the plane in between the chlorine, oh, let me change colors here, and we put the plane in line with the chlorine and the bromine and that center carbon, we see that we get a hydrogen on each side as a mirror image of it, and therefore it has a plane of symmetry. Okay, so requirements for chiral carbons are four different things bonded to carbon. And if you find a plane of symmetry in it, it becomes achiral. This becomes very important when we have more than one stereocenter. Okay, so questions on what a chiral compound is and what an achiral compound is. Okay, great. All right, so now, because chiral compounds have mirror images that are non-superimposable, the pair of compounds are what we call enantiomers. Okay, so enantiomers always come in pairs. You have the one isomer, and then you have the non-superimposable mirror image isomer, and that gives us our enantiomers. Okay, so the things to also look for here is you always look for the thing that has the four bonds to it, the four different things bonded to it. That's going to be the place where you're going to need to do the manipulation, and that's the one we're actually going to label as that stereo center. In this case here, when you're talking about stereochemistry, immediately look for the carbon with four different things attached to it. Mark it, in this case, with an asterisk, because that's the one you need to pay attention to. Okay. Now, another interesting rule is that if you have one stereo center, it is always chiral, because you will never be able to find a mirror plane in that system. However, if you have two stereocenters, it can actually wipe out chirality by finding that mirror plane. Okay, so if you only have the one chiral center, you're good to go. You have your pair of enantiomers, and if you have more than that, pause, look for a mirror plane of symmetry. Okay, now, why do we care about chirality? Okay, Well, it turns out the biological system of humans and plants and everything are very specific about which isomer it will process. And what it can do is actually process the two different isomers in a different way. For example, in ibuprofen, one of them is an active ingredient that gives you um, a pain relief, and the other is actually a liver toxin. So you have to make sure you only have one or the other. The other classical example is the one shown here. It's thalidomide. Thalidomide in its S isomer, and we'll talk about S and R later, um, actually is a really good sedative, and it was used to relieve birth morning sickness in pregnant women in the 1950s and 60s. Unfortunately, what they didn't know at the time was that the R isomer, which was made at the same time as the isomer, is actually what we call a teratogen. A teratogen causes birth defects. And so you'll hear maybe in some very old memes about thalidomide babies. This is because there was a mixture of the two. Half of the isomer wasn't a sedative, but caused birth defects. The other one was the sedative and actually worked. Okay. So since then, it's been pulled off the US market, but when they figured out it was the R and S derivative, they actually still sell the S derivative as a sedative, but they don't have the R in there, which is causing the birth defects. The other cool thing is that most plants or animals will only make one of the two possible isomers. Okay, it's very specific about the metabolic pathway. And so what you can have is certain plants will make a compound called limonene. Okay, some plants will make the S-limonene, and that has a lemon smell. Okay, and some plants will make the R-limonene, which is the orange smell. Okay, you'll probably actually interacted with the compound limonene because if you've ever used Goo Gone that smells like lemon or lemon pledge, it has limonene in it. Okay, it's a naturally occurring what we call terpenoid or terpene, and again, it's made by some plants as the S and by some plants as the R. And interestingly enough, our nose can tell the difference between the R and the S. Okay. Any questions on that? Okay. All right. Okay. So now I said you have to be careful when you have more than one stereo center because you have to look for that plane of symmetry. And this is what I mean. And notice the plane of symmetry doesn't actually have to cut through an atom. It can just cut through bonds. And in the case of this right here, we have a chiral center here and a chiral center here. First, let me prove to you that that's a chiral center. Okay. So we have the methyl group here, which is one group. We have a methylene with a methyl group, which is a second group. We have a carbon with a carbon and two hydrogens. That's our third group. And don't forget our hydrogen sticking down here, which is our fourth group. So we have four things bonded to that carbon. Therefore, it's our chiral center. It's the one we have to pay attention to. Okay. So now that we have that there, and interestingly enough, when we draw it such that we have this other methyl group attached, and it's also facing out of us with the page, facing out of the page toward us because of the dark wedges, we can actually draw a plane of symmetry, and this mirrors that, and this mirrors that. Therefore, we found a plane of symmetry, and this molecule is no longer chiral. It is achiral. Okay. We can also do it on things that have a sigma bond on them as well. If we draw our mirror plane here, we have the methyl groups are opposite each other, the hydrogens are opposite each other, and the OHs are opposite each other. So even though each of these carbons right here in red, had four different things bonded to it, the compound itself is not chiral. Okay, and what we'll find out is there's a name for that when we talk about these pairs, and it's called a meso compound. Okay. M-E-S-O. Okay, so then we can also, they don't have to be right next to each other. Here, the two chiral centers were right next to each other. They can actually be opposite each other, especially in symmetrical molecules, because we can find a plane of symmetry. So whenever you have symmetrical molecules, start looking for that plane of symmetry to determine whether your compound is achiral or does have chirality. Okay. So in this, you have half of your oxygen on one side, and we're assuming the hydrogen is going to be up here, so it's half of that. And each side mirrors itself, and therefore, even though this is up and this is down, the plane of symmetry is actually cutting through those bonds, and so it doesn't matter that they're in opposite directions. What matters is we found that plane of symmetry. Okay, questions on planes of symmetry? Okay. This becomes particularly important when we have 2 or more stereocenters. Okay, so let's start picking out our chiral carbons. Being able to recognize your chiral carbon is going to be one of the first things you do on the activity next week. So the first thing we do is look for 4 different things attached, okay? So let's look at this first one right here. And we have a CH2 bromine. Okay, that's different than this bromine. That's different than the CH2 CH3. Oh, but we have a CH2 bromine. And so it has a mirror image, but those mirror images are going to overlap each other because we have 2 of the same groups. So that means this is just one compound, and this is the exact same compound. So there's no reason to do it. Okay, and we can show this to ourselves by just taking our mirror image, rotating it 180 degrees, and seeing that the bromine lines up with the bromine, the ethyl group lines up with the ethyl group, this bromoethyl group lines up with this bromoethyl group, and this bromoethyl. So that's how we can identify this, is by drawing the mirror image, rotating it 180 degrees, and seeing if they are superimposable. If they are, it's not chiral. Okay, so let's do that same thing, but with a chiral compound to make sure that we're doing our process correctly. So the only thing we've done here is we've changed this to a methyl group. We've kept this as an ethyl group, this is a bromine, and this is the bromoethyl group here. So the first thing we do is draw our mirror image. And remember, the easiest way to draw your mirror image is draw your mirror and start from the group that's closest and keep the same stick or wedge that it has. We have our stick going up to an ethyl group, our dashed wedge going to our bromine, and our solid wedge coming out to our bromoethyl group. Okay. So then what we're going to do is we're going to take this and rotate it around 180 degrees. So this bromine right here, so this methyl group is going to be lined up with this methyl group. That's why we do 180 degrees. We're trying to get the ones that are in the plane of the paper to overlap first, and then we look for the other 2 groups. Okay, if we do that, we can take that, we can rotate. So this bromine is going to come out to the front, this is going to go to the back, and we're going to end up with, the bromine is going to go to the back, sorry, we're rotating it 180 degrees. And we're going to end up with our, this is drawn wrong. Okay, so, okay, I drew this wrong, I'm sorry. So this bromine, this methyl group is going to come down and be here, CH3. This ethyl group is going to stay up there because we're just rotating around that bond, CH2, CH3. This bromoethyl group is going to be back, CH2, CH2 bromine, and this bromine is actually going to come out to the front. Okay, so this is the wrong drawing here. But when we do that right here, we now have the bromine. So the ethyl group, the carbon, and the methyl group all line up together. But now the bromine is swapped with the ethyl bromide, and the ethyl bromide is now swapped with the bromine. Okay, so let me, so yeah, that is drawn wrong. I apologize. Questions on that? So the process is draw your mirror image, rotate it 180 degrees, and see if all the groups line up. If they line up, then it is not chiral. Okay. Okay. Questions? Okay, let's go here. So now we know what stereoisomers are. We know that our stereocenters have 4 different things, and we know that they are non-superimposable mirror images of each other. So now we have to identify which is which. Since we have 2 different chemical compounds and our nomenclature says we have to have a unique naming system for each and every chemical compound, we are coming up with the R and S system to assign which is which. All the other part of the chemical name, the prefix, infix, suffix, are all going to be exactly the same. The only change is going to be what's at the beginning of it, and it's either going to be an R or an S, okay? So we're going to use those same rules we used for E and Z to assign priority. Okay, so In this case here, we're going to go through those rules again. Start with atomic number, okay? So oxygen has a higher atomic number than carbon or hydrogen, therefore it's going to be our first priority. So we can assign that as priority 1 right here. The next is we have a carbon and a carbon. Those are the same. We have to go out 1. And here we have a carbon and 2 hydrogens. So that's going to give us this priority. We have a carbon with 3 hydrogens, which gives us this priority. The one with a carbon on it is the higher priority now. So it's given us our 2. This is then our 3, and hydrogen is usually 4, okay? If you have 2 hydrogens on there, it's not chiral anyway, but hydrogen's always our lowest priority, okay? So we've assigned priority based on our first rules, okay? Now, I'm gonna show you 2 ways to do this. This is the way the book does it, and some people like it a lot because of the ability to do the rotation, but you do have to turn it and redraw it sometimes. I have a question. So why doesn't the CH2CH3 do the 180? Oh, the one on the top? Because you're rotating around that axis. So the CH2CH3 on the top of that structure we drew we're actually rotating around that axis, and so everything else flips around, but that stays in the same location. We only want to rotate one axis. We don't want to spin it around like that, okay? So the way the book shows is actually a really good method, but you have to redraw it. So the way we do it is you first assign priority, okay? So in this case here, we've assigned priority and we've redrawn it. So 2 of the groups are coming out of the page. One of the groups is going back into the page, okay? And one of the groups is in the plane of the paper, okay? But we have to redraw it so that the lowest priority thing is the only one going into the paper, going behind the paper. So we have to redraw it so our lowest priority has the wedge. And in this case, what it's going to do is we're going to rotate this molecule 120 degrees, which brings our OH out and our methyl group up. So we're going to have our OH on this side, our methyl group on this side, and our lowest priority backwards. Okay. So we're going to have 2 things out, 1 thing down, and our lowest priority going into the plane of the thing. Now, once we've done that, we look at the order of the priority. Okay, in this case, we have 1, 2, 3. And if we draw a line with that, it's going in this direction, and that is clockwise. Okay, so when we have something where we have our priorities 1, 2, 3 in a clockwise fashion with our 4th group going back into the page, we have what we call our rectus or right, which is our R configuration. Okay, if it went counterclockwise, we would have the Latin word is sinister or left, and therefore we would have the S designation. So if it's clockwise, you assign it the R enantiomer. Okay. So let's do that again right here with the 2 different enantiomers of this 2-butanol, okay? So, and the way we do this is we take the one we have, and in this case, we have the R2-butanol right here. And the way it's drawn, we want to make it a mirror image of it. So we're going to start with our mirror plane, and we're going to hydrogen first. The methyl group has a dashed wedge. The OH has a solid wedge, and our ethyl group goes down. Okay, so now we've created our mirror image. In theory, it should be the other half of our enantiomer. And in theory, it should also be the S isomer. Okay, so we have to assign it R and S. So what we're going to have to do is we're going to have to take our new compound we just drew, and we're going to have to redraw it such that our hydrogen is facing back. Okay, so to redraw it such that our hydrogen is facing back, I think it needs to rotate 120 degrees this way, which puts the OH group over here and the methyl group over here. Okay, so do we see where that rotation is around? Again, we're using the center carbon and one of the groups as the axis we're turning on. And all we're doing is rotating all the other groups so that the lowest priority is the dashed wedge behind the paper. Okay, when we do that, we end up with this structure here. So we see the OH is on this side, the methyl group is on this side, and both of those are coming out at us. and our hydrogen's our lowest priority. So now let's do our count. We have OH is 1, this carbon is 2, this carbon is 3. That means we're going in a counterclockwise condition, which turns it into our sinister or left or S configuration. Okay. Now the cool thing is, once you assign one of the enantiomers, the other one's always going to be the opposite, because there are non-superimposable mirror images. So that is how you would find, number one, draw the other isomer, and number two, assign the other isomer. Okay. Let's see, I think, okay, and I'll show you something else on that. Okay, now I want to show you another trick if you don't like this. This is, you kind of have to redraw it to make sure you get it right. I'll show you a way you don't have to redraw it and you use your hand, okay? Left hand, right hand, doesn't matter. You just have to assign things correctly, okay? So what I'm gonna do is I'm going to take this one right here, the R isomer here, and I'm gonna show you how to use your hand to do assignment, okay? So when you have your hand to do assignment, what you're gonna do is you're gonna put the lowest priority where your wrist is, okay? Always the lowest priority on the wrist, and you align your hand so that it matches the molecule. In this case right here, hydrogen is my lowest priority, okay? And so I'm gonna rotate my hand slightly so I can put my methyl group here, okay? See, because it's coming out at me. I'm gonna put my OH group there because it's coming out at me, and my thumb is gonna be number 2, okay? So 1, 2, 3. So now all I have to do is take it and look at it and go 1, 2, 3. That is clockwise, therefore it's the R configuration. Okay. So that's another way to do it that doesn't involve redrawing. And the cool thing about that is that you can start with it in any configuration. For example, let's do this one right here, okay? So I'm gonna put my hand like this because my H is sticking out at me, okay? My OH is coming out at me. My methyl group is down here and my ethyl group is down here, which gives me 1, 2, 3, 1, 2, 3. And then I look at it and it's going clockwise, and that's our R isomer. Okay. So what I'd like you to do is what I would like you to do is to pick one of those two different things and practice it and use it when we do our activity on Tuesday. Okay. Try not to do both of them because flipping back and forth. My son is texting me. Stop texting me. He's in the other room, sorry. Okay. All right, so those are our rules. Those are 2 ways to do our assignment. And let's do our last rule for assignment, which is the double bond rule, okay? So let's look at this compound here, okay? So when we have a chiral compound, the first thing we look for is, where is the carbon with all the different things on it, okay? And in this case here, we have a carboxylic acid group, we have an OH group, we have, hydrogen, we have this methoxy hydroxy group here and a nitrogen, okay? So that means we have 4 different groups, which means this is our stereo center. That's where we're gonna do it. So the first thing we're gonna do is now assign priority. So let's see, we have a carbon, a hydrogen, and a carbon, and a nitrogen, okay? So which one's the highest? The chat's open. Which one's the highest priority of this set?
The nitrogen.
Nitrogen, that's right, because it is atomic number 7, carbon's atomic number 6, therefore it's our highest priority. So this is our priority 1, okay? So then we have a carbon and a carbon, but we have to, they both have oxygens bonded to them. So let's do our multiple bond rule and say, okay, this carbon right here has 1 oxygen bonded to it for this, 1 oxygen bonded to it for the first bond, 1 oxygen bonded to it for the second bond. So that's its priority right here. Now let's look at this carbon down here. We have 1 oxygen on it and a hydrogen and a hydrogen. Okay, so now we know that this one is higher priority than this one because it has a total of 3 oxygens bound to that same carbon. So that makes this 2, which makes this 3, which makes that 4. Okay, so we've used our last rule of prioritization to assign our priorities. And we know where our chiral carbon is. And now we have to assign it, okay? This is where that trick of your hand works really well, because what we can do is we can order our hand like this with our hydrogen facing back at us, and the OH is the closest to us, so we can assign that as number 3. The nitrogen is number 1, so that would be the middle finger, and then the carboxylic acid is going to be number 2. So it's 1, 2, 3, 1, 2, 3. That is clockwise. So I think that's the R isomer. Okay, but let's do it the other way too, to make sure that we did it right. This is the R isomer. So in this case here, because the hydrogen's facing down here, we actually have to rotate the entire molecule 180 degrees. We're just going to rotate it in the plane of the paper like this. And when we redraw that, we have a hydrogen back there. Let's see, this is going to go from this side to this side. So we're going to have a heavy wedge with the OH on it out here, because it's right here. We're rotating it like that. And then the nitrogen is going to come out at us with a heavy wedge right here. Nitrogen. And then that carboxylic acid group is going to go down here. And notice it's in the plane of the paper still. It was in the plane of the paper beginning, and all we've done is rotate it such that that nitrogen and that OH have come out. So now let's use the rule in the book right here. This is our number 4. This is our 1, 2, and 3. And that is going in a clockwise fashion. Therefore, it is R. Okay. So I've shown you 2 methods to find R and S. Pick one and practice. Okay. All right. Okay. And again, the prioritization we use with the multiple bonds is here if you want a greater explanation. And it is R. Yay. Okay, so there's a lot of different ways to draw these chiral carbons, but the most important thing is you must be precise about their 3-dimensional place in space. So most of the time we're going to draw it in a way that's such that we have wedges to give it 3-dimensionality. If you just draw 4 things with all flat lines, we don't know how it's attached. We don't have that. So you must always draw them with the wedge system. And I like the tetrahedral wedge system right here, but some people don't. And so they actually draw it where the bottom part's in the plane, and that's fine too. And you can do it in a cross-like configuration if you draw the 2 opposing ones in the same type of wedge. So notice both of those are going down, both of these are coming up, and only the center carbon is actually in the plane of the paper. Any of these drawings is appropriate because it shows us its 3-dimensionality. Okay, questions on that? Okay, so if this molecule is a mirror image of this molecule and they have all the same connectivity, and other than that place in space, they're identical, okay? Most of the time, both sets of enantiomers have exactly the same properties: melting point, boiling point, density. They bond the same way and everything like that. So how can we tell them apart? Okay, the cool thing about chiral compounds is they interact with light in such a way that they can rotate the light as the light goes through the system. Now, most light is kind of scattered going in all different directions. And what I mean by that is that light's a wave, right? So it kind of does this, right? So the axis in which the amplitude is changing here is its polarization, okay? So if we have one piece of light going like this and another piece of light going in the opposite, like this, those are perfectly good planes, but they're not polarized. They're not a way we can use them. So what we can do is we can take the light that's going in all different directions and we can put it through a polarizer. And we put it through a polarizer, all the light coming through the polarizer are all aligned. And we call this plane polarized light, okay? The cool thing about this plane polarized light is when it starts to interact with that chiral molecule, because it's different in space, it has an electronic and a magnetic component. And so what we'll see is this plane polarized light, well, as it goes through the sample, will start to rotate, okay? And this is called optical rotation, okay? It's going to rotate to the left or the right, and we can measure this. And when we measure this, that gives us an idea that, number one, we have a chiral compound. Number two, we might have a pure chiral compound because it's rotating that light. So we do this by measuring the activity on what we call a polarimeter. So we have a source of light that puts out all sorts of, all different planes of light. We go through a polarizer such that it all lines up. Then you shoot it through a sample of your material. And then as it interacts with that sample, it rotates. And then there's another polarized light at the end where you rotate it around till it gets to the maximum intensity. And when it's at its maximum intensity, that's the amount of rotation the molecules rotated that plane polarized light, and we can measure that. Okay. So this is how we know it works right here. And the other thing is that if it was an achiral molecule, it's not going to rotate polarized light. So we know that that's going to happen. And the optical activity of a substance, like if you have one enantiomer, one of the pure enantiomers, it's going to rotate light in one direction and one direction only. Cool thing is, the other enantiomer is going to be in the equal and opposite direction. Okay, so when we talk about the observed rotation, it's the one you measured, but then we have to standardize it so everybody can have the same thing. So another way to think about this is that when the light is rotated clockwise, we call that dextrorotatory, and we signify that with a plus because it's going in the positive clockwise direction. If it actually rotates the light counterclockwise, we denote that with a negative sign, and we call that lavorotatory, okay? A lot of times in biological systems like sugars and stuff, you'll actually see the little d and the little L in front. That little d in front means it rotates light in the positive direction, and the L means it rotates light in the negative direction. So you'll see that a lot, especially in biology and biochemistry. But dextrorotatory is right, lavorotatory is left, clockwise. Dextrorotatory is clockwise, lavorotatory is counterclockwise. Okay, so to make sure that my observed rotation can be shared with other people, we actually have a standardized process. So we need to look at the shape, the type of the molecule, the concentration, how long the cell was you did it, what the wavelength of light was, what the solvent, and what the temperature, because they all change a little bit. And so if I want to compare my data to yours, we have to have a specific notation that lets us all be sharing the same amount of data. And we call that specific rotation, okay? So specific rotation is usually this alpha in a bracket. And when we have our alpha in a bracket, we have our temperature, we have our wavelength of light, and that tells us that we have standardized it so it's all going to, so that we can compare data. Now notice that's equal to the observed rotation, the length of the cell times the concentration, okay? So we've taken out any variation in length, we've taken out any variation in concentration, and so that my number of -23 is going to match your number of -23, even though we measured it at different concentrations, okay? So we also have to do it by temperature, and I'll explain that in a little bit. So typically we do it in temperature in degrees C. We use a wavelength of light. Most common is what we call the sodium D line. When you excite electrons out of the sodium atoms, they emit into what we call the 589 nanometer range, and that's a very common one to use. The alpha, again, is the observed rotation, and then we have the length, usually in decimeters, okay? So that's 10 centimeters. So most polarimeters actually have a 10 decimeter cell, so that is 1 decimeter. And then concentration in grams per milliliter. The most common concentration to use is 1 gram per 100 milliliters, because 100 milliliters fits into a 1 decimeter size sample holder. Okay, so, and that specific rotation, once you've calibrated for all the different variables, is a constant, a physical constant, just like boiling point and melting point. Okay. So, all right, so I know how to assign R and S now. And that means that I know which direction of the light it's going to change, right? Unfortunately, no. There's no straightforward correlation between R and S. So One compound can have an R that is dextrorotatory or positively tilted. Another compound can have a negative tilt. So there's no specific way, you have to measure it. Okay. But the other cool thing is that notice the two isomers here have equal and opposite rotations. Okay. So pure isomers will have a equal and opposite rotation. In this case, the S is going clockwise and has that positive 23.1 degrees of rotation. The R is equal and opposite, so it's negative 23.1 degrees rotation. Okay, questions on that? Okay, now we also have to note the temperature because depending on how it's interacting with a solvent, it can change. So an extreme example of that is this aminosuccinic acid is at room temperature, rotates light counterclockwise, lava rotatory. And once you heat it up to 100 degrees, it actually rotates light in the other direction. So that's why temperature is kind of always important. And it's usually done at 20 to 25 degrees C. Okay, so if I have a pure enantiomer, it's going to rotate light in one direction. If I have the other enantiomer, it's going to rotate light in the other direction. But if I have a mixture of the two, and they're the same concentration, this one's going to try to rotate light clockwise, this one's going to try to rotate counterclockwise, and it cancels it out. So it has a net optical rotation of 0. And we call this a racemic mixture. So it's often, if you haven't purified it such that you have the R or the S, but you know you have a chiral center, you denote it by having that plus and minus at the beginning, right here, saying you don't have the R 2-butanol, you don't have the S 2-butanol, you have a mixture of R and S 2-butanol, and it's denoted by that plus and minus. Okay. All right, so if we can have a racemic mixture and equal portions cancel each other out, what if we don't have equal portions? Okay, if we don't have equal portions, that means we have one enantiomer in excess of the other enantiomer. Okay, so that means that, well, let's say we have only 5 of these and we have 10 of these. Okay, so that means that 5 of these are going to cancel out 5 of these, but we're still going to have a measurable rotation because the other 5 can still rotate that light. Okay, so the 2 enantiomers that are in the same concentration start canceling each other out, and that means we have one of the enantiomers in excess, and so we call it enantiomeric excess. And we can calculate that with a percentage by saying the moles of one enantiomer minus the moles of the other enantiomer divided by the total moles, and that should give us the number that we should see for our specific rotation observed for that mixture. And so that means we can actually do the other calculation, which would be the observed specific rotation divided by the specific rotation of a pure enantiomer. We can also get the enantiomeric excess. So it's not that we have 25% of it is one compound, therefore we're going to have 75% of the rotation. It doesn't work that way because the ones that are equal and opposite cancel each other out. So we're only looking at the molecules above and beyond the canceling each other out, giving us an optical rotation. So what does that look like? Okay, so in a simple sense, if we had our pure butanol, S-butanol right here, they are all going to rotate light in the clockwise direction, hence the S right here, and I'm sorry, the plus mark here. So our S, excuse me, our S enantiomer is going to rotate light clockwise. It's not always that way, but it's that way. And we're going to see 100% of its optical activity because it's the pure enantiomer. So when we actually measure it, it measures out to positive 13.52 degrees. So pure S-butanol has a specific rotation of 13.52. Okay. So that's 100% of those molecules. Okay. So let's start mixing in a little bit of the R right here. And in the R, those are going to rotate it lava rotatory, which means that this R is going to cancel out this S, This R is going to cancel out this S, and this R is going to cancel out this S. So only the remaining, what is that, 14 equivalents of the S are going to rotate light. Okay, so that means we're only going to get a percentage of that light rotation because we've wiped out 6 whole possibilities there. And so what we'll see is we get about 70% is the enantiomeric excess. And so when we measure it, we actually get 70% of the pure optical rotation. So in this case, it's going to measure out at 9.46 degrees. Okay, but that's 70% of the enantiomeric excess. But if we looked at the percent of the molecules as a total, we actually have 85 mole percent is the positive, 15 mole percent of the negative. Okay, but this 15% knocks out 15% of this, taking it down to 70% that are active and measured. Do we see how that works? Okay, I'm going to explain it one more time with another example here. So if we take it and we add a little bit more, so now we have 5 equivalents of our R, we have 15 equivalents of our S, we will see an optical activity of 50% because these are all canceling each other out. 50% of the material in there is canceled out. Only 50% actually rotates light. And therefore, we end up with 1/2 of our pure specific rotation at that 6.76%. But let's look at that mole percent. That mole percent was 75 because we had 15 of one and only 5 of the other, which gives it 25. So we have to take out 25% of this to take it down to 50. That's the only ones that are active, and that's why it's a 50% enantiomeric excess. Okay, so we do that again. If we get a 50-50 mixture, 10 R's, 10 S's, that's going to cancel all of each other out, and we're going to end up with a net 0. And by definition, that 50-50 mixture is our racemic mixture. Okay, and we can do the same thing by going and adding the S to the R, and we'll see the same but equal and opposite effect. Notice that our pure one is a negative 13.52, and our mixtures are negative numbers as well. Okay, questions on enantiomeric excess? Okay, so the key here is that you can tell when you have it pure because it'll have the specific rotation of measured, and you can tell when you have a mixture because it either has no optical activity or some percentage of the pure. And by knowing the percentage of the pure, you can get the molar equivalence of each of the components. All right, so, all right, take a break, breathe. Okay, so that was easy. We had one stereo center. We could identify it. We know how to do R and S. We have 2 different methods, the hand method or the paper method. What if you have more? Well, turns out that whenever you have more than one stereo center, your number of isomers is exponential, okay? And it's 2 to the n being the number of stereo centers. So if you have 2 stereo centers, it's going to be 2 to the 2, which is equal to 4. If you have 3 stereo centers, that's 2 to the 3, which is 8. And if you have 4 stereo centers, 2 to the 4 is 16. So right away, you can get to a lot of different isomers, okay? And I'm going to show you a way to, number 1, identify how many isomers you have and how to draw the other isomers so that you can start with one of the compounds with 2 stereo centers and draw all the other isomers available to you. Okay, so what's really cool is that, let's say you have something like cholesterol, which has 8 stereo centers in it, okay? Which means there's 256 possible isomers of it, but biological systems being very precise, you only make 1 isomer of it in your body. and you only use one isomer of it in your body. So chirality is important. Okay, so the first thing we want to do is we want to say we now have to have a new classification. Okay, enantiomers always come in pairs. Okay, so if we have equal and opposite, mirror images of each other that non-superimposable, that's a pair of enantiomers. Okay, but we have a total of 4 isomers possible in our 2 stereocenters. Now, the other set, those 2 other ones, also have to be enantiomers of each other. But these are not non-superimposable mirror images to those. And these are not superimposable mirror image to those, which means that that set of 4 isomers is now called a set of diastereomers. Think of di as having 2 or more stereocenters, diastereomers. Okay. So when we look at this, we're going to have to draw, given a single compound here, we're going to have to figure out how to, number 1, draw its enantiomer, and number 2, how to draw the other isomers possible. Okay, and I'm going to show you a trick for that. And we're going to be using a thing called the Fischer projection. Okay, so I'm actually going to jump down to the Fischer projection first and then come back to the diastereomers. Okay, in a Fischer projection, we are making it easier for us to see the 2 different stereocenters and see where they are. And the way we do that is we draw out 4 straight lines, but we do it in a specific pattern. Okay, so the first thing we do is we take our nice tetrahedral geometry we have here and rotate it such that only the central carbon is in the plane of the paper. And we have 2 going down, and the 2 going down are in the x-axis of our paper. And then we have 2 coming up, and that's going to be in the x-axis of our paper, and then the 2 going down are on our y-axis of our paper. And we do it that same way every time. Okay, and the reason we do that in the same way every time is because the next thing we're going to do is we're going to draw just straight lines. Now, but we have to remember that this is the one that's going to be going down. These are the ones that are going to be coming up. And that's what we have in our Fischer projection. And that allows us to draw multiple stereocenters all at the same time and still be able to see them. Okay, so that's our Fischer projection. So anything in the up-down axis here is in the plane of the paper or behind, and anything going side to side is coming, okay, behind, and anything coming side to side is going to be a solid wedge. Okay, so that's what our Fischer projection is. Okay, so let's go back to where we were and look at these right here. So the other cool thing about the Fischer projection, it makes us easier to make our mirror images as well. So let's start with this set over here. Oops. This set over here. And when we draw our Fischer projection, remember this is our dashed wedge, this is in the plane of the paper, this is our dashed wedge, and then these are solid wedges coming out at us. Okay. So we're going to draw our mirror image exactly the same way we did with the other one, but we don't have to use our wedges. Okay. So what we're going to do is we're going to draw our mirror, and we're going to start at our mirror and basically draw the same thing. So our hydrogen is going to be first, then our carbon, and then our bromine as we're going out this way. Our methyl groups are going to be here, and we're going to start this way and go bromine, carbon, hydrogen, and then our ethyl group stays here. Now we can, because these are not chiral, we just have to note that it's there. We don't have to actually have it in the plane. So with this, we have 2 stereocenters, and we've just been able to use that mirror plane to create the enantiomer. Okay, so these are equal and opposite enantiomers. These are non-superimposable pairs. Okay, and the way to also think about that is, okay, on one enantiomer, I have a bromine and a hydrogen lining up on one side and on the other side, and then I have the opposite set on the other ones, but it's still a hydrogen bromine and a hydrogen bromine on each side of the molecule. Okay. So that's important because how do we get to our other isomer? To get to our other isomer, what we have to do is start with our original thing and swap two of the groups. We're going to swap this bromine and this hydrogen right here, and that's going to give us our first enantiomer of the other set. Okay. Notice it is not, if we swap those two, it is not now the mirror image of this one, so it's completely different. So that's how we get to our next set of isomers, is we swap two, just two of at one carbon. Now, when we do that, we ended up with our bromines are now on the same side, right here, and our hydrogens are on the same side. Okay, so these are not superimposable with that. They are not mirror images of that. Okay, so that being said, now we know we have a different compound, and we need to draw it such that we have its enantiomer, its mirror image. And so we're going to do the same thing we do. I'm going to draw our mirror plane and start bromine, carbon, hydrogen, bromine, carbon, hydrogen, bromine, carbon, hydrogen, bromine, carbon, hydrogen, and methyl group and ethyl group. So we've been able to draw our mirror image. Okay. See, that's the joy of the Fischer projection, is that it's very simple to draw, but it has enough information in it that you know where everything is. Okay. Okay. So again, to stress a point here, this pair is a pair of enantiomers, and this pair is a pair of enantiomers. The set of both set pairs are diastereomers. Okay, questions on that? Okay, now we can also use a trick to help us assign R and S with our system here as well. Okay. Oh, no, I'm going to show you another example of that. So unlike enantiomers, which have the exact same physical properties except for that rotational light, the two different sets of enantiomers, of the two different sets in the diastereomers, actually can have different physical properties, and they can be separatable. So this pair right here is not separatable because they are enantiomers. This pair right here is not separatable by physical means because they are enantiomers. However, if you take one of one and one of the other, these are diastereomers. You can separate that set because they might have different boiling points, melting points, solubilities, etc. So that is a very important fact in that diastereomer definition, is because they're not superimposable in our images, they are different compounds and they are separable. Separable. Okay, so how do we name these? Well, what we have to do is we have to do what we do for all of our other nomenclature. We assign the longest parent chain, we put on the lowest substituent, and then we now have numbered carbons for where our chiral carbons are, okay? And we now have to assign each carbon its correct system. Now for this one, this is actually one where you can redraw it like the book, but I'm gonna do it with my hand because I like that. And what I'm gonna do is I'm actually gonna use my left hand because the hydrogen's already sticking out at us. And so I'm gonna have to orient my hand such the hydrogen's sticking out of this. The bromine's closest to me, the methyl group's back, and this is in the plane. So we have bromine, ethyl, methyl, bromine, ethyl, methyl, bromine, ethyl, methyl, which is counterclockwise when I look at it here, and therefore it's S. So that means our number 2 carbon here, our number 2 carbon here, oops. Our number 2 carbon here is S configuration. And I just use my hand for that. If you want to go back and do the other one, that's down here. Okay. But now let's do the 3 carbon here. So we're going to do 3 carbon again. We're going to do, okay, I'm going to orient my hand so that my wrist here is my methyl group again. And then we have, let's see, we have it going back and in the plane and back and forward. Let's figure out how we can orient my hand. So, okay, we have something, these two coming out at me, this one going up. So we have down, we have bromine, we have carbon and we have the other carbon. So that is going around there, giving us the R clockwise, yeah, giving us R configuration. So that means our second carbon, our carbon 3, is the R configuration. Okay, so let's put that all together and name this compound. So what we're going to do is we have, let's see, 1, 2, 3, 4, 5 carbons. So we have pentane. We have no alkenes, so it's pentane something. We have 2 substituents with our bromine. The bromines are on the 2 and the 3 carbons, so that's 2, 3 dash dibromopentane. But now we have to assign the carbons. And the way we do that is we take the carbon number 2 and put an S next to it because our 2 carbon was assigned S. And we take our 3 carbon and assign it R. So our full name is going to be bracket 2S, 3R, bracket dash 2, 3 dash dibromopentane. Okay. So the cool thing is once you have one of those diastereomers assigned, the other one is going to have the opposite. So, and I want you to go back and prove it to yourself that it's true, that if this was S here, if we draw its mirror image over here, this is now R. And if we draw the mirror image, this carbon here is now transitioned. This one's now S. So go back and practice either one of the 2 things, and you can see that those have swapped places and give us R and S. Now, when we go to the other pair of enantiomers, notice the bromines are on opposite sides on this one. We have to go back and reassign. And on this one, our 2 carbon is an R. Our 3 carbon is also an R. Notice that in our first pair, they were opposite, equal and opposite right here. In the other pair, that means they're going to have to be, at least one of them has to be switched because one of them has to be switched. So in the other set, it's going to be RR, and in this case, it's going to be SS. So we can see a pattern in diastereomers where one is going to be RS, the other is going to be SR, and then the other set of diastereomers is going to be RRSS. Okay, let's see what we got here. 3 minutes. And we already talked about Fischer projections. Okay. So this becomes really helpful when we start looking for planes of symmetry. Okay. The Fischer projection allows us to do a lot of work with that plane of symmetry. So for example, if we were to draw it as wedges and stuff, you're like, oh, draw a plane here, draw a plane here. You know, no, that looks all the same, right? Well, if we redraw it to go to the eclipsed form, so we have the longest hydrocarbon chain being down, and so the longest hydrocarbon chain here is going to be the y-axis. It's going to go up and down like this, and then we're going to add our substituents right here. So see how these methyl groups were right here. These 2 carbons are in the plane. So this is our long axis. This is our y-axis. And then our OHs were on the back. So when we do that, they're on this side. But remember, in a Fischer projection, anything going to the sides is solid wedges. Anything going up and down is in the plane or going back. Okay, so now we have this. So now we draw it as our true Fischer projection. And now we look for a mirror plane. So we can draw a mirror plane here. We have OH, OH, methyl group, hydrogen, hydrogen. We have a mirror image. Okay, that makes this an achiral compound. But let's do the same thing for the other isomer. We have this. Oh, I think I can draw a mirror plane here. Maybe it's like, well, maybe not. So what we're going to do is we're going to translate it. So we have our longest hydrocarbon chain in a straight line, and we're going to orient that in the y-axis here, which is right here. And so we had a hydrogen on the top and an OH on the bottom. So we have a hydrogen on top, OH on the bottom. We have an OH and a hydrogen, so that's OH and hydrogen, which gives us this. So now if we draw our mirror plane here, they're no longer equal. We have a hydrogen and an OH. We draw a mirror plane here, we have a hydrogen and an OH. If we try to draw a mirror plane here, we have different things. So the Fischer projection allows us to see where those mirror planes are. This is a chiral compound and will rotate light. This is an achiral compound, even though we have two chiral centers. Notice we still have to identify the chiral centers, but the fact that we have that plane of symmetry makes it optically inactive, makes it an achiral molecule. Okay, I'm going to stop right there. And we're going to finish up this chapter, start a little chapter 6, and do our activity on Tuesday. Okay? I'll email that out Monday afternoon so you have time to play with it. All right, any questions? Okay, I'm going to go ahead and stop recording because we're right at time. And if you want to hang back and ask questions, please do.